Tonight we are going to sink, not in the way of falling, but in the way of settling, like sediment through water, down into the deepest places on Earth. The ocean covers more than 70% of our planet's surface, and yet we know more about the surface of Mars than we do about the floors of our own seas. This is not a failure of curiosity. It is simply the nature of the deep ocean to resist us, to remain hidden beneath layers of water so thick and heavy that sunlight itself cannot penetrate. Imagine standing at the edge of the sea on a clear morning. The water near the shore is perhaps 10 feet deep, maybe 20. You can see the bottom. You can see rocks and sand, and the shadows of fish moving in patterns that suggest thought, or at least intention. The water here is part of what oceanographers call the epipelagic zone, the sunlight zone, where light reaches and where most of the ocean's familiar life resides. This is the ocean we think we know, the ocean of beaches and boats, and the gentle rocking of waves that carries us to sleep on summer nights. But this zone extends only to about 200 meters beneath the surface. 200 meters, in the scheme of the ocean, this is nothing. This is the thinnest skin of water covering something vast and strange. The average depth of the ocean is about 3,700 meters. In the deepest trenches, the ocean floor lies more than 11,000 meters below the surface. To put this in perspective, if you placed Mount Everest, the tallest mountain on Earth, into the Mariana Trench, the deepest point in any ocean, the peak would still be covered by more than 2,000 meters of water. Let us begin our descent. We will move slowly, the way a diver exhales and sinks, or the way a particle of organic matter drifts downward in what marine biologists call marine snow. We leave the sunlight zone. The water grows cooler against our skin. The light begins to change. It is no longer the bright, scattered light of the surface, but something more directional, more blue. Red wavelengths are the first to disappear. They are absorbed by the water molecules within the first few meters. Then orange, then yellow. By the time we reach 30 meters, the world is painted in shades of blue and green, a palette narrowing with every meter of depth. At 200 meters, we cross an invisible boundary. We enter the twilight zone, the mesopelagic, where the sun's light becomes a memory rather than a presence. Here, between 200 and 1,000 meters deep, there is still light, but it is faint. It is the kind of light you might see in a room at dusk when you have not yet turned on the lamps, and you can still make out shapes, but not colors. Your eyes begin to adjust. You realize that seeing in this place requires a different kind of attention. The pressure increases. At the surface, the atmosphere presses down on us with a force of about 14.7 pounds per square inch. We do not notice this because we are built for it. Our bodies calibrated to this particular weight of air. But water is much heavier than air. For every 10 meters we descend, the pressure increases by 1 atmosphere. At 100 meters, the pressure is 11 times what it is at the surface. At 1,000 meters, it is 101 times. The human body, unprotected, would not survive this. Our lungs would collapse. The gases in our blood would behave in ways that would damage tissue and nerve. But we are not diving. We are imagining. We are sinking in the way of thought, and so we can continue without fear, moving deeper into the mesopelagic, where strange shapes begin to appear. These are fish, though not the kind you would recognize from the surface. Their bodies are built for a world of pressure and faint light. Many of them are small, no longer than your hand. Many have large eyes, disproportionately large, evolved to capture every available photon. Some have photophores, organs that produce light through chemical reactions, creating bioluminescence. Bioluminescence is not magic, though it appears that way. It is a chemical process. Inside specialized cells, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. The reaction releases energy in the form of light. Different species produce different colors, usually blues and greens, because these wavelengths travel furthest in water. The light serves many purposes. It attracts prey, it confuses predators, it communicates with potential mates. In the twilight zone, where the sun's light is failing, life has learned to make its own. We continue downward. The temperature drops. Near the surface, ocean water might be as warm as 30 degrees Celsius in tropical regions, pleasant enough to swim in without a wetsuit. But temperature in the ocean is stratified, layered like a cake, and we are moving through those layers. At around 200 meters, we often encounter a thermocline, a boundary where temperature shifts rapidly. Below this line, the water grows cold. At 1,000 meters, it hovers around 4 degrees Celsius, just above freezing. The cold is part of the pressure, part of the darkness, part of the architecture of the deep. At 1,000 meters, we cross another boundary. We leave the mesopelagic and enter the bathypelagic, the midnight zone. The name tells you what you need to know. There is no sunlight here. None. The only light comes from the creatures themselves, from their bodies, their bioluminescent lures and signals glowing in the black. This zone extends from 1,000 meters to 4,000 meters deep, and it is the largest habitat on Earth by volume. More of the planet is midnight zone than anything else. The creatures here are adapted to total darkness. Many have lost their eyes entirely. There is no evolutionary advantage to maintaining eyes when there is nothing to see. So over millions of years, those structures have diminished or disappeared. Other fish have developed eyes so sensitive they can detect the faintest bioluminescent glow from hundreds of meters away. Some have tubular eyes, pointed upward, watching for the silhouettes of prey, backlit by the faint glow from above. The food supply is scarce. At the surface, phytoplankton use sunlight to photosynthesize, converting carbon dioxide and water into glucose and oxygen. They form the base of the ocean's food web. Zooplankton eat phytoplankton. Small fish eat zooplankton. Larger fish eat smaller fish. But photosynthesis requires light, and there is no light in the midnight zone. So the creatures here survive on what falls from above: the marine snow, the bodies of dead organisms and fecal matter, and bits of organic tissue drifting downward like a slow, constant rain. This means that life in the bathypelagic is sparse. The fish are often small. Their metabolisms are slow. They can go weeks or months without eating. When they do encounter food, they must consume as much as possible, and so many deep-sea fish have evolved enormous mouths and expandable stomachs. The gulper eel, for instance, has a mouth larger than its body, capable of swallowing prey of equal size. It looks like a nightmare, but it is simply a solution to the problem of hunger in a place where meals are rare. We sink further still. At 4,000 meters, we enter the abyssopelagic, the abyssal zone. This zone extends down to 6,000 meters and covers vast areas of the ocean floor. The pressure here is crushing, more than 400 times the atmospheric pressure at sea level. The temperature is just above freezing. The darkness is absolute, and yet life persists. The abyssal plains are not mountains or valleys, but flat expanses of sediment, muddy floors that stretch for thousands of kilometers. Occasionally, the remains of a whale will sink to this depth, an event called a whale fall. When this happens, it creates a temporary ecosystem. Scavengers arrive first, hagfish and sleeper sharks that tear into the flesh. Then come worms and crustaceans that consume the remaining tissue and bones. A single whale carcass can sustain life for decades. Below 6,000 meters lies the Hadal zone, named after Hades, the ancient Greek underworld. This is the deepest part of the ocean, found only in trenches where tectonic plates meet and one is forced beneath the other. The Mariana Trench, the Tonga Trench, the Philippine Trench. These are the true abysses, places where the ocean floor drops away into chasms that seem almost planetary in scale. Thoughtful tone. At these depths, the pressure exceeds 1,000 atmospheres. At 11,000 meters in the Challenger Deep, the deepest known point in the Mariana Trench, the pressure is approximately 8 tons per square inch. This is the weight of 50 jumbo jets pressing down on an area the size of your thumbnail. And yet, in 1960, 2 men descended to this depth in a bathyscaphe called the Trieste. They looked out through a small porthole and saw a flatfish lying on the sediment. Life, even here. The descent is complete. We have traveled from the sunlight zone, where colors are bright and life is abundant, through the twilight and midnight zones, where light fades and creatures glow, into the abyssal plains, where the ocean floor is silent and still, and finally to the Hadal trenches, where the earth itself seems to fall away into darkness. This is the vertical architecture of the ocean, a structure of pressure and light and temperature that divides the water into distinct realms, each with its own rules, its own forms of life. And now that we have descended, now that we understand the layers, we can begin to explore what lives in these depths and what the geography of the deep looks like. But first, let the journey settle. Let the pressure equalize. Let the darkness become familiar. We are at the bottom of the world, and there is no rush to return to the surface. We have time. We have all the time we need. The floor of the deep ocean is not smooth. It is not a simple, flat expanse of mud and sediment, though there are plains that stretch for distances that would take days to cross, even in a submersible. The ocean floor is in fact a landscape as varied and dramatic as any on land. There are mountains taller than the Himalayas. There are canyons deeper than the Grand Canyon. There are volcanic ridges that wrap around the planet like seams on a baseball, and trenches that split the crust of the earth like wounds. Let us begin with the mid-ocean ridges. These are underwater mountain ranges formed by the movement of tectonic plates. The Earth's crust is not a single solid shell. It is divided into large sections called plates that float on the semi-molten rock of the mantle beneath. These plates are constantly moving, though very slowly, at rates measured in centimeters per year. Where 2 plates move apart, magma rises from the mantle to fill the gap. This magma cools and solidifies, forming new crust. Over millions of years, this process creates a ridge, a raised seam where new ocean floor is being born. The Mid-Atlantic Ridge is perhaps the most famous of these features. It runs down the center of the Atlantic Ocean, roughly parallel to the coastlines of the Americas on one side and Europe and Africa on the other. It is more than 16,000 kilometers long, and, in some places, it rises more than 2,000 meters above the surrounding ocean floor. If the Atlantic were drained, you would see a mountain range that dwarfs anything on land, a spine of rock running from the Arctic to the Antarctic. But the ridge is not just a mountain. It is an active geological feature, a place where the Earth is literally pulling itself apart. Along the crest of the ridge, there are fissures, cracks in the crust where magma wells up and cools in contact with seawater. The temperature difference is extreme. The magma can be over 1,000 degrees Celsius. The seawater is near freezing. This interaction creates unique geological formations, including something called black smokers. Black smokers are hydrothermal vents, chimneys of mineral deposits that rise from the ocean floor and emit superheated, mineral-rich water. The water is heated by magma beneath the crust, then forced upward through cracks. As it rises, it dissolves minerals from the surrounding rock. Sulfides are metals like iron, copper, and zinc. When this hot, mineral-laden water meets the cold ocean, the minerals precipitate out, forming solid particles that look like black smoke. Over time, these particles build up around the vent, creating a chimney that can grow several meters tall. The water emerging from a black smoker can be as hot as 400 degrees Celsius. At the surface, water boils at 100 degrees. But at the depths where these vents are found, the pressure is so high that water remains liquid at much higher temperatures. The superheated water does not boil, it simply rises, carrying with it a payload of minerals and chemicals that would be toxic to most life on Earth. And yet, around these vents, life thrives. This is one of the great discoveries of deep-sea exploration. In 1977, scientists in the submersible Alvin descended to a mid-ocean ridge near the Galapagos Islands and found hydrothermal vents surrounded by dense communities of organisms. There were giant tube worms, some over 2 meters long, their red plumes waving in the current. There were clams and mussels with shells the size of dinner plates. There were crabs and shrimp and fish, all living in close proximity to the vents. This was unexpected. The prevailing theory at the time was that all life on Earth depended, ultimately, on sunlight. Even in the deep ocean, the food chain was thought to trace back to photosynthesis in the sunlit surface waters. But the vent communities were too dense, too vibrant, to be sustained by the meager trickle of organic matter from above. There had to be another energy source. That source is chemosynthesis. Instead of using sunlight to convert carbon dioxide and water into glucose, certain bacteria use the chemical energy in hydrogen sulfide, one of the compounds emitted by the vents. These bacteria oxidize hydrogen sulfide, a process that releases energy, and they use that energy to fix carbon and produce organic molecules. The bacteria form the base of the vent ecosystem. The tube worms, which have no mouths or digestive systems, harbor these bacteria in specialized organs called trophosome. The bacteria provide the worms with nutrients. The worms provide the bacteria with hydrogen sulfide, absorbed from the water through their plumes. This is a fundamentally different form of life. It is life that does not depend on the sun, life that has found a way to harness the chemical energy of the Earth itself. The discovery of vent communities changed our understanding of where and how life can exist, and it expanded the possibilities for life elsewhere in the universe, on moons and planets where sunlight is scarce, but geological activity might provide an alternative energy source. Beyond the ridges and vents, there are the trenches. These are the deepest parts of the ocean, long, narrow depressions formed where one tectonic plate is forced beneath another in a process called subduction. The Mariana Trench, the deepest known trench, is located in the Western Pacific. It is a crescent-shaped scar in the ocean floor, over 2,500 kilometers long, and at its deepest point, nearly 11,000 meters below sea level. To descend into a trench is to enter a place that feels almost extraterrestrial. The walls are steep, the floor is narrow, the pressure is immense, the water is cold and still. There is no light except what you bring with you, and even that seems swallowed by the darkness, absorbed as quickly as it is emitted. The sediment on the trench floor is soft, a mixture of clay and the remains of microscopic organisms that have drifted down from the surface over millennia. The organisms that live in the trenches, the Hadal zone, are called piezophiles, lovers of pressure. They are specially adapted to survive under conditions that would kill most other forms of life. Their cells contain molecules that stabilize proteins under high pressure. Their bodies are often small and gelatinous, lacking gas-filled spaces that would collapse. Some species of snailfish, for instance, have been found at depths exceeding 8,000 meters. They are pale, almost translucent, with soft bones and bodies that feel almost liquid to the touch. The trenches are also home to amphipods, small crustaceans that resemble shrimp. In the Mariana Trench, amphipods the size of your hand have been captured in baited traps. They scavenge on whatever organic matter reaches the trench floor, including the occasional animal carcass or piece of wood. Their metabolism is slow. They move slowly. They reproduce slowly. Time, in the trenches, seems to operate at a different pace. Between the ridges and the trenches, there are the abyssal plains. These are the vast, flat regions that make up the majority of the deep ocean floor. They are covered in sediment, layer upon layer of fine particles that have settled over millions of years. The sediment is made of clay minerals, silica from the shells of diatoms, calcium carbonate from the shells of foraminifera, and tiny fragments of rock and organic matter. The plains are not entirely featureless. There are seamounts, underwater mountains that rise from the ocean floor but do not break the surface. These are often extinct volcanoes, remnants of volcanic activity that occurred millions of years ago. Some seamounts rise thousands of meters, creating isolated habitats where ocean currents are diverted upward, bringing nutrients from the deep. These upwellings support communities of fish, corals, and sponges that would not otherwise exist in the surrounding abyssal plain. There are also abyssal hills, smaller elevations that cover large portions of the ocean floor. These hills are typically only a few hundred meters tall, but they are numerous, and together they create a landscape that is gently undulating rather than perfectly flat. The hills are thought to be the most common landform on Earth, covering more area than any mountain range or plateau on land. And then there are the canyons. Submarine canyons are steep-sided valleys that cut into the continental slope, the boundary between the shallow continental shelf and the deep ocean floor. These canyons can be as deep as 1,000 meters and as wide as several kilometers. They are often formed by underwater landslides or by the erosion caused by turbidity currents, dense flows of sediment-laden water that rush down the slope like underwater avalanches. The Monterey Canyon, off the coast of California, is one of the largest and best-studied submarine canyons in the world. It is deeper than the Grand Canyon and extends over 100 kilometers from the continental shelf to the abyssal plain. The canyon acts as a conduit, channeling organic matter from the surface waters down to the deep, and this makes it a hotspot of biological activity. Researchers have found deep-sea corals, sponges, sea stars, and fish living on the canyon walls and floor. The architecture of the deep ocean is shaped by forces that operate on timescales we struggle to comprehend. The movement of tectonic plates occurs over millions of years. The accumulation of sediment on the abyssal plains occurs grain by grain, layer by layer, over eons. The formation of a seamount begins with a volcanic eruption that might last only a few years, but the mountain itself persists for tens of millions of years, slowly sinking as the crust beneath it cools and contracts. This is a landscape that is ancient and active, both. It is being created and destroyed simultaneously. New crust forms at the ridges. Old crust is consumed at the trenches. Mountains rise and erode. Canyons are carved and filled. The ocean floor is not a static stage on which life plays out. It is a dynamic participant, shaping the conditions that determine where life can exist and what forms it can take. And so, when we think about the deep ocean, we must think not only about the water and the darkness and the pressure, but also about the rock and sediment beneath. We must think about the vents that provide energy where there is no sunlight. We must think about the trenches that create pockets of extreme conditions. We must think about the seamounts that rise like islands in the abyss, creating refuges for creatures that cannot survive on the plains. The architecture of darkness is not empty. It is not featureless. It is a landscape as rich and varied as any on Earth, and it is inhabited by forms of life that have adapted to its particular challenges. And now, having explored the geography, we turn our attention to the inhabitants themselves, to the creatures that have made the deep ocean their home. In the deep ocean, there are no seasons. There is no spring or summer, no autumn or winter. The temperature does not fluctuate with the angle of the sun or the passage of months. The darkness is constant. The pressure is constant. And yet, life has found a way to exist here, to persist in conditions that seem, at first glance, incompatible with living systems. The creatures of the deep ocean are adapted to their environment in ways that can seem strange to us, accustomed as we are to the surface world. They have evolved under selective pressures that are entirely different from those on land or in the sunlit waters above. Food is scarce, light is absent, the pressure is immense. And so, the forms that life has taken are often unlike anything we encounter in our daily experience. Let us begin with the anglerfish. The anglerfish is, in many ways, the iconic creature of the deep. There are more than 200 species, and most live at depths between 200 and 2,000 meters in the twilight and midnight zones. The female anglerfish, which is the larger of the sexes, has a modified dorsal fin that extends forward over her head like a fishing rod. At the tip of this fin is a lure, a fleshy bulb that contains bioluminescent bacteria. The bacteria produce light, and the anglerfish uses this light to attract prey. In the darkness of the deep ocean, a small, glowing object is irresistible to many creatures. Small fish and crustaceans, drawn by curiosity or hunger, approach the lure. When they come close enough, the anglerfish opens her enormous mouth and sucks them in with a sudden rush of water. Her teeth are long and needle-like, angled backward to prevent escape. Her stomach is expandable, allowing her to consume prey that is as large as herself. The male anglerfish is much smaller than the female, often less than a tenth of her size. In some species, the male's entire life strategy revolves around finding a female. When he does, he bites into her skin and releases an enzyme that dissolves the tissues of his mouth and her body at the point of contact. Over time, the two circulatory systems fuse. The male becomes a permanent parasite, receiving nutrients from the female's bloodstream. In return, he provides sperm whenever she is ready to reproduce. This adaptation, called sexual parasitism, is a solution to the problem of finding a mate in the vast, dark ocean. The chances of a male encountering a female are vanishingly small, and so when the opportunity arises, he commits entirely. He gives up his independence, his organs atrophy, and he becomes little more than a sperm-producing appendage. It is a strategy that seems extreme, but in an environment where encounters are rare, it is effective. Another deep-sea creature that captures the imagination is the giant squid, Architeuthis dux. For centuries, the giant squid was the stuff of legend, a sea monster that appeared in sailors' tales and ancient maps. But in the modern era, dead specimens have washed ashore or been caught in fishing nets, and we know now that the giant squid is real. It can grow to lengths of over 13 meters, with eyes the size of dinner plates, the largest eyes of any animal on Earth. Those enormous eyes are an adaptation to the deep ocean. They allow the squid to detect the faintest traces of bioluminescence, which might indicate the presence of prey or predator. The giant squid hunts at depths of several hundred meters, using its two long feeding tentacles to capture fish and smaller squid. The tentacles are lined with suckers, and each sucker is ringed with sharp, tooth-like structures that grip the prey and prevent it from escaping. Despite its size and fearsome appearance, the giant squid is elusive. Very few people have seen a living giant squid in its natural habitat. The first footage of a giant squid in the wild was captured in 2004 by Japanese researchers who used a baited line and a camera. The squid was filmed at a depth of 900 meters, and the video shows a creature that is both alien and graceful, moving through the water with slow, deliberate motions. The deep ocean is also home to many species of jellyfish and related organisms called siphonophores. One of the most remarkable is the Portuguese man-o'-war, though it is more accurately classified as a colonial organism, a collection of specialized polyps that work together as a single entity. Some polyps form the float, which drifts on the surface. Others form the tentacles, which trail below and can extend for tens of meters. Still others are responsible for digestion or reproduction. But deeper than the Portuguese man-o'-war, at depths of several thousand meters, live other siphonophores that are even stranger. The giant siphonophore, Apolemia, holds the record for the longest animal ever recorded. In 2020, researchers in a remotely operated vehicle discovered an Apolemia specimen off the coast of Australia that was estimated to be 46 meters long. It formed a spiral in the water, a delicate lace-like structure that pulsed gently with bioluminescent light. The siphonophore captures prey with its tentacles, which are armed with stinging cells called nematocysts. When a small fish or crustacean brushes against the tentacle, the nematocysts fire, injecting venom and entangling the prey. The captured organism is then pulled toward the digestive polyps, which secrete enzymes to break down the tissue. The nutrients are shared among all the polyps in the colony. Many deep-sea fish have adaptations that seem almost supernatural. The barrel-eye fish, for instance, has a transparent head. Inside the transparent dome are two tubular eyes that point upward, watching for the silhouettes of prey against the faint light from above. The eyes are extremely sensitive and can detect even the smallest movements. The fish's body is dark, but the head is clear, allowing light to pass through without scattering. The viperfish is another creature that seems designed for a nightmare. It has a long, slender body and teeth so large they do not fit inside its mouth. When the viperfish closes its jaws, the teeth curve outward, creating a cage from which escape is nearly impossible. The viperfish hunts by swimming rapidly through the water, mouth open, impaling prey on its teeth. It also has photophores along its body that produce light, possibly to attract prey or to communicate with other viperfish. Then there is the gulper eel, Eurypharynx pelecanoides. The gulper eel has a mouth that is disproportionately large compared to its body. The jaw can open wide enough to swallow prey of equal size. The body is long and whip-like, ending in a tail that glows with a pink bioluminescent organ. The function of this tail light is not fully understood, but it may attract prey or serve as a lure. The deep ocean is also home to many species of octopus. The Dumbo octopus, named for the ear-like fins that protrude from the sides of its head, lives at depths of up to 7,000 meters. It is a small octopus, usually no more than 30 centimeters in length, and it moves by flapping its fins or by pulsing its webbed arms. The Dumbo octopus is a benthic predator, feeding on worms, crustaceans, and other small invertebrates that live on the ocean floor. One of the most fascinating aspects of deep-sea life is bioluminescence. It is estimated that up to 90% of the creatures living in the deep ocean can produce light. This light is not for vision in the way we think of it. It is for communication, camouflage, and predation. Some fish use counter-illumination, producing light on their undersides to match the faint glow from above, making them invisible to predators looking up from below. Others use flashing patterns to signal to potential mates. The cookie-cutter shark, a small species that grows to about 50 centimeters in length, uses bioluminescence in a particularly clever way. The underside of the shark is covered in photophores that glow with a greenish light, matching the ambient light from above. But there is a dark collar around the shark's throat that does not glow. From below, this collar looks like the silhouette of a small fish. Larger predators, such as tuna or dolphins, approach to investigate, and when they do, the cookie-cutter shark darts upward and bites, removing a circular plug of flesh with its specialized teeth. There are also creatures that seem almost transparent. The glass octopus, for instance, has a body that is nearly invisible in the water. Only its eyes and digestive tract are visible, appearing as small, dark shapes floating in the void. This transparency is a form of camouflage. In the absence of places to hide, the best strategy is to become invisible. The deep ocean is a place where the usual rules of biology seem to bend. Fish have antifreeze proteins in their blood to prevent ice crystals from forming in the near-freezing water. Some organisms have copper-based blood instead of iron-based, which is more efficient at transporting oxygen in cold, high-pressure environments. Many species have slow metabolisms, allowing them to survive on very little food for extended periods. The lifespan of deep-sea organisms can be extraordinarily long. The Greenland shark, which lives in the deep, cold waters of the North Atlantic and Arctic, is believed to be the longest living vertebrate on Earth. Radiocarbon dating of the eye lenses of several individuals suggests that they can live for over 400 years, possibly as long as 500. They grow slowly, perhaps a centimeter per year, and do not reach sexual maturity until they are over 100 years old. The deep ocean is also home to many species that we have only recently discovered, and doubtless many more that we have not yet encountered. In 2005, a census of marine life found over 5,000 new species in the deep ocean. In 2010, researchers discovered new species of snailfish in the Peru-Chile Trench at depths of over 7,000 meters. In 2012, filmmaker James Cameron descended to the bottom of the Mariana Trench in a submersible and filmed sediment, rock, and small amphipods on the seafloor. Each new expedition, each descent into the deep, reveals something unexpected. A fish with a body plan unlike any known species. A jellyfish with a new form of bioluminescence. A worm that lives inside a hydrothermal vent, tolerating temperatures and chemical concentrations that would be lethal to most other forms of life. The deep ocean is, in this sense, a frontier, a place where our knowledge is incomplete and our assumptions are regularly challenged. The inhabitants of the deep ocean are not separate from the surface world. They are part of a global ecosystem. Organic matter from the sunlit surface waters sinks and feeds the creatures below. Some deep-sea fish migrate vertically, rising to shallower waters at night to feed, and descending to the depths during the day to avoid predators. Whales dive to great depths to hunt for squid and fish, then return to the surface to breathe. And yet, the deep ocean remains largely inaccessible to us. We cannot live there. We can only visit, briefly, in submersibles or remotely operated vehicles. We rely on cameras and sensors to tell us what is happening in a place we cannot directly experience. And so, our understanding of the deep ocean is mediated by technology, by the instruments we build and the data they collect. But even with these limitations, we can appreciate the ingenuity of life, the way it has adapted to fill every available niche, even in the most extreme environments. The creatures of the deep ocean are a testament to the resilience of biology, to the capacity of living systems to find solutions to seemingly impossible problems. They remind us that life is not confined to the comfortable, sunlit places. It exists in the cold and the dark and the crushing pressure, in forms that are strange and beautiful and entirely their own. When we think of the deep ocean, we often imagine silence. We picture a place so remote, so separated from the noise of human activity that it must be quiet in a way that is almost absolute. And in some ways, this is true. There is no wind in the deep ocean, no rustling of leaves, no birdsong, no traffic. There is no surface for sound to echo against in the way it does in a canyon or a concert hall. The deep ocean is insulated from the cacophony of the surface world. But the deep ocean is not silent. It is full of sound, though not the kind of sound we are accustomed to hearing. Sound in the ocean behaves differently than sound in air. Water is much denser than air, and this density allows sound to travel faster and farther. In air, sound travels at about 343 meters per second. In seawater, it travels at about 1,500 meters per second, more than 4 times as fast. This means that a sound produced on one side of an ocean basin can, under the right conditions, be detected on the other side. The speed of sound in water is not constant. It varies with temperature, salinity, and pressure. Warmer water transmits sound more quickly than colder water. Saltier water transmits sound more quickly than fresher water. Higher pressure increases the speed of sound. These variations create layers in the ocean where sound behaves in interesting ways. One such layer is called the SOFAR channel, which stands for Sound Fixing and Ranging Channel. The SOFAR channel is a horizontal layer in the ocean, usually at a depth of about 1,000 meters, where the speed of sound reaches a minimum. This occurs because the effects of temperature and pressure balance each other. Above the SOFAR channel, the water is warmer, which increases sound speed. Below it, the pressure is greater, which also increases sound speed. In the channel itself, sound is trapped. It refracts or bends back toward the channel whenever it tries to escape upward or downward. This means that sound produced in the SOFAR channel can travel for thousands of kilometers with very little loss of energy. During the Cold War, the United States Navy installed a network of underwater microphones called hydrophones to listen for submarines. These hydrophones were positioned in the SOFAR channel, and they could detect the sounds of ships and submarines from across entire ocean basins. The same principle is used today by scientists to study whale songs, underwater earthquakes, and the movements of icebergs. Whales are among the most vocal inhabitants of the ocean. The songs of humpback whales are perhaps the most famous. These songs are complex, patterned sequences of moans, cries, and clicks that can last for 10 to 20 minutes and are often repeated for hours. The purpose of these songs is not fully understood, but they are produced primarily by males during the breeding season, which suggests they may function as mating calls or territorial displays. Humpback whale songs change over time. Each population has its own song, and within a population, the song evolves from year to year. New phrases are added, old phrases are modified or dropped. This cultural transmission of song is rare in the animal kingdom, found in only a few species, such as certain birds and whales. It suggests a level of social complexity and communication that we are only beginning to understand. Blue whales, the largest animals ever to have lived on Earth, produce some of the loudest sounds in the ocean. Their calls can reach 188 decibels, louder than a jet engine. These calls are low frequency, usually between 10 and 40 Hz, which is below the range of human hearing. But these low frequencies travel extraordinarily long distances in water, and it is possible that blue whales can communicate with each other across entire ocean basins. The function of these calls is not entirely clear. They may help whales maintain contact with each other over vast distances. They may play a role in navigation, allowing whales to create mental maps of the ocean based on the echoes of their calls, bouncing off underwater mountains and other features. They may serve as social signals, conveying information about identity, location, or reproductive status. In the deep ocean, where light does not penetrate, sound becomes the primary means of sensing the environment. Many deep-sea creatures use sound to navigate, to hunt, and to communicate. Dolphins and toothed whales use echolocation, emitting clicks and listening for the echoes that bounce back from objects in the water. The time it takes for an echo to return tells the animal how far away the object is. The quality of the echo provides information about the object's size, shape, and texture. Sperm whales, which dive to depths of over 2,000 meters to hunt for squid, produce the loudest biological sounds of any animal, clicks that can exceed 230 decibels. These clicks are focused into a narrow beam by the spermaceti organ, a structure in the whale's head filled with waxy oil. The clicks are used for echolocation, allowing the whale to locate prey in the complete darkness of the deep ocean. But sound in the ocean is not always biological. There are many natural sounds that have nothing to do with living organisms. Earthquakes generate low-frequency rumbles that travel through the ocean. Underwater volcanoes produce hisses and explosions. Icebergs carving from glaciers create loud cracks and groans as they break apart and enter the water. Rain falling on the surface creates a pattering sound that can be heard underwater. Even the movement of sand and sediment on the ocean floor, stirred by currents, produces a faint, continuous noise. And then there are the sounds made by humans. Ships produce constant noise from their engines and propellers. This noise is concentrated in the low-frequency range, the same range used by many whales for communication. As shipping traffic has increased over the past century, so too has the ambient noise level in the ocean. Studies have shown that in some parts of the ocean, the noise level has doubled every decade. This increase in noise has consequences for marine life. Whales must call louder to be heard over the background noise, which requires more energy. In some cases, whales may alter their behavior, avoiding noisy areas or changing their migration routes. There is also evidence that intense noise, such as that produced by military sonar or seismic surveys for oil and gas, can injure or disorient marine mammals, leading to strandings and deaths. The deep ocean is also filled with sounds that we do not fully understand. In the 1990s, hydrophones, Pacific Ocean detected a sound that was dubbed the bloop. It was a low-frequency sound, much louder than any known biological source, and it was detected by sensors over 5,000 kilometers apart. At the time, some speculated that it might be produced by an unknown species of giant squid or other deep-sea creature. However, analysis of the sound's characteristics suggests it was most likely produced by an icequake, the fracturing and movement of large icebergs. There are other mysterious sounds as well. The upsweep is a long-lasting, persistent sound that has been detected in the Pacific since the 1990s. It is a tonal sound that rises slightly in frequency over time, and it is seasonal, being more prominent in certain months. The source is unknown, though it may be related to volcanic activity or the movement of the seafloor. The Julia sound, detected in 1999, is another enigma. It is a brief, loud sound that sweeps upward in frequency. It was recorded by the NOAA Equatorial Pacific Ocean Autonomous Hydrophone Array, and it was powerful enough to be detected by multiple sensors over a range of several hundred kilometers. Like the bloop, it is now thought to be related to ice, possibly the sound of an iceberg running aground or colliding with another iceberg. These sounds remind us that the ocean is a dynamic environment, full of processes that are difficult to observe and even more difficult to understand. The deep ocean is not a static, unchanging place. It is alive with movement and activity, much of it invisible to us, but detectable through sound. For the creatures that live in the deep ocean, sound is essential. It is how they navigate, how they find food, how they communicate with each other. In the absence of light, sound provides the information they need to survive. The ocean is a three-dimensional space, and sound allows animals to sense objects and other animals in all directions, at distances that would be impossible to achieve with vision alone. But sound in the ocean is also affected by human activity in ways that are not always obvious. The noise from ships, for instance, is not just a local problem. Because sound travels so far in water, the noise from a single ship can affect marine life over a wide area. Seismic surveys, which use powerful air guns to create sound waves that penetrate the seafloor and reveal geological structures, can be heard by whales and other animals hundreds of kilometers away. There is a growing recognition that we need to manage the soundscape of the ocean, just as we manage air quality or water quality on land. This means reducing noise from shipping, perhaps by designing quieter propellers or by routing ships away from sensitive habitats. It means regulating the use of sonar and seismic surveys in areas where marine mammals are known to congregate. It means acknowledging that sound pollution is a real and serious threat to ocean life. The ocean is not silent, but it should not be deafening either. There is a balance to be struck, a way of coexisting with the ocean's inhabitants that respects their need for a relatively quiet environment. And as we learn more about how sound shapes the lives of marine animals, we have an opportunity to make better decisions, to reduce our impact, to allow the ocean to retain its natural acoustic character. In the deep ocean, far from the noise of shipping lanes and coastal development, there are still places where the soundscape is dominated by natural sources. The calls of whales, the rumble of earthquakes, the crackling of shrimp, and the clicking of dolphins. These sounds have been part of the ocean for millions of years, long before humans ever set sail. And perhaps there is something to learn from the silence that exists between the sounds. In the deep ocean, there are moments of quiet, intervals when no whale is calling, no earthquake is rumbling, no iceberg is cracking. These moments are not empty, they are full of potential, full of the possibility of sound. They are the pauses between notes in a piece of music, the spaces that give the notes their meaning. The deep ocean teaches us that silence is not the absence of sound. It is the presence of listening. It is the state of being attuned to the environment, ready to detect the faintest signal. For the creatures of the deep, this attentiveness is a survival skill. For us, it is an invitation to pay attention, to listen more carefully, to recognize that the ocean is speaking to us in ways that we have only just begun to understand. We have descended through layers of water, explored the geography of the ocean floor, met the creatures that inhabit the depths, and listened to the sounds that fill the darkness. And now, as we prepare to return to the surface, it is worth considering what the deep ocean means to us, not just as a physical space, but as an idea, a concept that shapes how we think about knowledge, mystery, and our place in the natural world. The deep ocean is, in many ways, the last great unknown on Earth. We have mapped the surface of Mars and Venus with greater resolution than we have mapped the ocean floor. We have sent probes to the outer planets and beyond. We have telescopes that can detect galaxies billions of light years away. And yet, less than 20% of the ocean floor has been mapped in detail. The rest remains largely unexplored, known only in the most general terms. This is not because we lack curiosity or ambition. It is because the ocean is difficult to explore. The pressure makes it dangerous. The darkness makes it hard to see. The vastness makes it impossible to survey comprehensively with the resources we have. A single expedition to the deep ocean can cost millions of dollars and involve years of planning. Even then, the amount of ocean floor that can be examined in a single dive is tiny, a few square kilometers at most. And so, the deep ocean remains mysterious, not in the romantic sense of ancient maps that labeled unknown regions with the phrase, "Here be dragons," but in the sense that it contains genuine unknowns. There are species we have not yet discovered. There are geological features we have not yet mapped. There are processes and interactions we have not yet observed. The deep ocean is a place where our ignorance is not a temporary condition to be remedied with a little more effort, but a structural reality that will persist for the foreseeable future. This raises a question. What does it mean to live in a world where there are still places we cannot fully know? In an age where information is abundant and accessible, where we can search for answers to almost any question with a few keystrokes. The deep ocean stands as a reminder that not everything is knowable, at least not yet, and perhaps not ever. There is a philosophical tradition that values mystery, that sees the unknown not as a problem to be solved, but as something to be appreciated in its own right. The philosopher Immanuel Kant wrote about the sublime, the feeling we experience when confronted with something so vast or powerful that it exceeds our ability to comprehend it fully. The ocean, especially the deep ocean, is sublime in this sense. It is larger than we can imagine, deeper than we can easily visualize, and more complex than we can fully grasp. But the sublime is not just about scale. It is also about the way the unknown challenges our assumptions and expands our sense of what is possible. Every time we descend into the deep ocean and discover something new, a fish with a body plan we have never seen before, a geological feature that does not fit our models, a form of life that uses an energy source we had not considered, we are reminded that nature is more creative than we are. This is humbling. It is a reminder that our theories and models are approximations, useful tools for making sense of the world, but not the final word on how things are. The deep ocean teaches us intellectual humility, the recognition that our knowledge is incomplete and that there will always be more to learn. But there is also something comforting about the existence of the unknown. It means that the world is not exhausted, not fully catalogued and filed away. It means there are still frontiers, still places where discovery is possible, still opportunities to be surprised. The deep ocean is one of those places, and its existence enriches our world, even if most of us will never visit it directly. The deep ocean also raises questions about value. How do we value something we cannot use, cannot see, and can barely access? The creatures of the deep ocean are not economically important in the way that fish stocks or coral reefs are. They are not tourist attractions. They do not provide obvious ecosystem services. And yet, there is a sense in which they matter, in which their existence has value, simply because they exist. This is a value that is intrinsic rather than instrumental. It is not based on what the deep ocean can do for us, but on what it is in itself. The philosopher Aldo Leopold articulated this idea in his Land Ethic, arguing that we should recognize the right of all parts of the natural world to exist, not because they are useful to us, but because they are part of the community of life to which we also belong. The deep ocean, in this view, is valuable because it is a functioning ecosystem, a community of organisms that have evolved together over millions of years. It is valuable because it is beautiful, even if that beauty is hidden in darkness and accessible to only a few. It is valuable because it is complex and mysterious, and because it represents possibilities that we have not yet imagined. But recognizing this value is not easy. It requires a shift in perspective, a willingness to care about things that do not directly affect our daily lives. It requires an imagination that can extend beyond the immediate and the visible to encompass the remote and the hidden. It requires, in other words, a kind of empathy, a recognition that the deep ocean is not just a resource or a curiosity, but a place that is alive in its own right. This empathy is being tested as human activity begins to reach into the deep ocean in new ways. There is interest in mining the ocean floor for minerals, particularly in areas where manganese nodules and other metal-rich deposits are found. These nodules form over millions of years and are concentrated on the abyssal plains. They contain cobalt, nickel, and other metals that are used in batteries and electronics. The companies that want to mine these nodules argue that they can do so with minimal environmental impact, using remote-controlled machines to vacuum up the nodules and leaving the surrounding seafloor largely undisturbed. But scientists who study the deep ocean are skeptical. The abyssal plains are not lifeless deserts. They are home to communities of organisms that depend on the nodules and the sediment around them. Disturbing the seafloor could disrupt these communities in ways that are difficult to predict. There is also the problem of the sediment plume. When nodules are collected, sediment is stirred up and suspended in the water. This plume can drift for hundreds of kilometers, settling on areas far from the mining site and smothering the organisms that live there. The long-term effects of this kind of disturbance are unknown, and once mining begins, it may be impossible to stop or reverse the damage. The question of whether to mine the deep ocean is not just a technical question about feasibility or profitability. It is a moral question about what we owe to the rest of the natural world, about whether we have the right to exploit resources in places we barely understand, about how we balance our needs and desires against the needs and existence of other forms of life. The deep ocean also challenges us to think about time in different ways. On the surface, we are accustomed to rapid change. Seasons come and go, weather shifts from day to day, plants grow and die within months or years. But in the deep ocean, time moves more slowly. The Greenland shark lives for hundreds of years. The accumulation of sediment on the abyssal plains occurs over millennia. The formation of a seamount takes millions of years. This slower pace of time means that recovery from disturbance is also slow. If a mining operation destroys a community of organisms on the abyssal plain, it could take decades or centuries for that community to recover, if it recovers at all. The deep ocean does not heal quickly. It does not forget. And so, the consequences of our actions in the deep ocean may persist long after we have moved on. There is a term in environmental ethics called intergenerational justice, which refers to the obligations we have to future generations. The idea is that we should not consume or destroy resources in a way that prevents future people from enjoying them. This principle applies to the deep ocean. The decisions we make today about whether to mine the seafloor, whether to reduce noise pollution, whether to protect certain areas from human activity, will affect the ocean that future generations inherit. But intergenerational justice is hard to practice. It requires us to think beyond our own lifetimes, to care about people we will never meet, to sacrifice immediate benefits for the sake of long-term sustainability. It requires, in other words, a kind of moral imagination that does not come naturally to us. We are creatures of the present, attuned to the needs and desires of the moment. Thinking about the deep future, about the world that will exist 100 or 1,000 years from now, requires an effort. And yet, the deep ocean invites us to make that effort. It is a place that operates on geological timescales, where processes unfold over millions of years. It is a reminder that the present moment is just one point in a much longer story, and that the choices we make now will reverberate into the future in ways we cannot fully predict. The deep ocean also raises questions about exploration and discovery. Why do we explore? What do we hope to find? The motivations for ocean exploration have varied over time. In the 19th century, expeditions like the HMS Challenger voyage were driven by a desire to understand the natural world, to catalogue its diversity, to test theories about the origins of life. In the 20th century, much of the exploration was driven by military and economic interests, by the need to locate resources or to track submarines. Today, ocean exploration is motivated by a mix of scientific curiosity, environmental concern, and technological ambition. We explore the deep ocean to understand how ecosystems function, to discover new species, to learn about the geology and chemistry of the seafloor. We explore to assess the impacts of climate change, to monitor the health of ocean habitats, to identify areas that should be protected. We explore because the ocean is part of our planet, and understanding it is part of understanding ourselves. But there is also a sense in which exploration is valuable for its own sake, not because it leads to useful knowledge or practical benefits, but because it satisfies a fundamental human curiosity about the world. We are explorers by nature. We want to know what lies beyond the horizon, what is hidden in the darkness, what exists in places we have never been. The deep ocean is one of the last places on Earth where this kind of exploration is still possible. And in exploring the deep ocean, we discover not only what is out there, but also something about ourselves. We learn about our capacities and our limits. We learn what it means to be a small, fragile creature on a vast planet. We learn to appreciate the complexity and diversity of life, and to recognize that we are just one species among millions. The deep ocean, in this sense, is a mirror. It reflects back to us our own curiosity, our own fears, our own hopes. It shows us what we value and what we are willing to sacrifice. It asks us to consider what kind of relationship we want to have with the natural world, whether we see ourselves as separate from it or as part of it, whether we approach it with humility or with hubris. There is a famous photograph taken from space called the Blue Marble, which shows the Earth as a sphere floating in the blackness of space. The oceans dominate the image, covering most of the visible surface. The photograph was taken in 1972 by the crew of Apollo 17, and it became an icon of the environmental movement, a reminder of the Earth's fragility and beauty. But the blue marble shows only the surface of the ocean, the sunlit waters where light and life are abundant. It does not show the depths, the layers of water that extend down kilometers below the surface, the trenches and ridges and plains that make up the majority of the ocean floor. The deep ocean is hidden in that photograph, invisible but present, a vast, dark space beneath the blue. And perhaps that is fitting. The deep ocean is, by its nature, hidden. It is a place that resists easy observation, that refuses to reveal itself fully. It is a place that demands patience, effort, and humility from those who seek to understand it. And in return, it offers something rare and valuable, a sense of wonder, a reminder that the world is larger and stranger and more beautiful than we often remember. As we prepare to return to the surface, to leave the deep ocean behind, it is worth carrying this sense of wonder with us. It is worth remembering that there are still places on Earth that are wild and mysterious, places that have not been tamed or fully understood. It is worth remembering that the ocean is not just a backdrop for human activity, but a living, breathing entity with its own rhythms and its own life. The deep ocean will continue to exist long after we are gone. The creatures that live there will continue to hunt and feed and reproduce. The vents will continue to emit their superheated water. The trenches will continue to deepen as tectonic plates shift and collide. The ocean does not need us, but perhaps we need it, not for resources or for recreation, but for the sense of perspective it provides, the reminder that we are part of something much larger than ourselves. And so, as we rise through the layers of water, as the pressure decreases and the temperature warms, as the first faint traces of sunlight begin to appear, we carry with us the memory of the deep. We carry the knowledge that beneath the surface there is a world of darkness and cold and pressure, a world inhabited by creatures that glow in the night, that sing songs across ocean basins, that live for centuries in silence. The deep ocean is a mystery, and it will remain a mystery for as long as we exist. But that is not a failure. It is a gift. It is a reminder that there is always more to discover, always more to learn, always more to wonder about. And in a world that often feels small and fully known, that gift is precious beyond measure. Let the ocean settle, let the darkness recede, let the pressure ease. We have been to the depths and we have returned. And in returning, we bring with us a sense of the vast, the strange, the beautiful, the unknown. The ocean is calling, even now, in the silence between waves, in the darkness beneath the surface. And if we listen, if we pay attention, we can hear it, we can feel it, we can know, in some small way, that we are connected to it, and it to us, in the great, mysterious dance of life on this blue planet.